In this video, we have a problem in which we're going to determine the electric field magnitude due to a couple of charges. We're going to utilize a superposition principle, which says that to find the net electric field, you can find the electric field from every charge individually and just add them up at the end. So let's go ahead and take a look at the problem statement. So here we have a sketch of the situation. We have in the xy plane two charges that are on the negative x-axis separated by a distance L. One of them is positive, one of them is negative. And on this graph over here, what we're told is that the electric field along the x-axis in the positive direction has particular values. It starts out very negative when you're very close to the origin, and then as you get further away, it becomes positive. What we're asked to find is the separation distance of the two charges, L, and we're also asked to find what is the maximum of the electric field, or rather, where is the maximum of the electric field on the positive x-axis? So where does that occur? Now, to get a kind of a feel for this, first let's kind of get an idea of what the fields look like along the positive x-axis. So let me remind us, first of all, that the electric field magnitude has a form that depends on the charges. In other words, the charge producing the field and the distance at which you're measuring the field away from where the charge exists. So what we're going to do is kind of compare the magnitudes of the fields produced by these two charges at different points along the positive x-axis, and that'll give us some idea of which direction the field points, and we can just verify that that's indeed what's given by this graph here. And then we'll go ahead to the computation. So let me just go ahead and redraw this axis here, the positive x-axis, and I'll just call that the origin. This is 10, 20, 30 centimeters, and we have the two charges, one at the origin and then one a little bit to the left of the origin. Now, let's compare the fields at a point that's very close to the origin, but a little bit to the right of it. So what we have is we have a field from the left-hand charge. This is a positive charge, so it's going to produce fields that point radially away from the charge, by definition. The fields will therefore point kind of in this direction at different points. And in particular, if you're along the x-axis, it's going to point away from the charge. So that field will point in the positive x-axis. Likewise, in this negative charge, the field will point towards it. So this charge will produce a field pointing in the negative x-axis. Let's first take a look at the field produced by this negative charge. Because we're very close to that charge over here, this 1 over r squared is going to be this quantity divided by a very, very small number. So it's going to be a very, very large quantity. In other words, it's going to have a very big field pointing in the negative x direction. Now for the positive charge, it actually has a larger charge because q1 over q2 equals 4. So you would think it may produce a larger field, but the r is going to be bigger in that case because you're further away from that particular charge, which means the 1 over r squared is going to be a little smaller. And actually, the 1 over r squared is more relevant here because you're squaring a very small quantity. You can get a very, very large number for the negative charge, so that's going to be more relevant here. And what that means is that the negative field produced by this charge is going to be much, much greater than the positive field produced by that charge because the r is so small there. So we're going to have two fields. This is going to be the field due to the negative charge. It's quite large and negative when you're very close to the origin. And then for the positive charge, it's going to be a little smaller. It's going to point in the positive direction. Okay. So the net field adding up these two vectors will point in the negative direction, which is what we see here in the graph. And now as we get further away, this 1 over r squared quantity is going to diminish very rapidly for the negative charge. And so the electric field won't be as large as you get further away. For this charge, the electric field will diminish also because you're increasing the distance you are from the charge as you get further away. But it won't diminish as rapidly, so you're going to have a little over here, you're going to have smaller fields from both of these guys. This one will diminish much more rapidly, so it'll eventually be about the same size as this field. And at some point, and it looks like here at x equals 20 centimeters, you should have a net field of 0, so you should have two electric field vectors pointing in opposite directions, canceling one another out, and that's what we see here. So that's what we expect there. And then as we get further away, the positive charge is bigger by 4 times than the negative charge, and that's going to become more relevant at longer distances. And so what that means is that when you're further away, the positive quantity will create a field that points in the positive x direction. The net field points in the positive x direction. All right, so that's kind of an idea of what the fields look like. And what we're going to do is utilize the fact that at x equals 20 centimeters, the net field is 0. And so what we need to find is an expression for the electric field as a function of x along the positive x-axis. And then in a moment, we'll set that equal to 0 when x equals 20 centimeters to solve for L. So what I want you to do on your own first is find out an expression for the electric field along the positive x-axis in terms of constants, in terms of the distance you are from the origin, in other words, x, in terms of L, and then in terms of one of the charges. So go ahead and find that out, and we'll come back and take a look, setting it equal to 0 at 20 centimeters to solve for L. All right, so for the field, you should find that the field is going to be a sum of two different parts. We're using superposition here. So the field from the positive charge is going to be its charge, which is Q1, and then you're dividing by the distance between, so if you're somewhere here on the positive x-axis, the distance that you are is going to be your x component plus that extra L. All right, and that's going to be positive because, as we noted, this is a positive charge. It's going to produce a field in the positive x direction. Now, for the negative charge, it's going to produce a field in the negative x direction. And its distance is only going to be x away because that's at the origin. So that distance is going to be x squared. All right, so that's what you get for the field. I want to write this in terms of just one of the charges. So I'll use the fact that Q1 over Q2 equals 4. So we can write the first term as 4Q2. And then we have this expression here, which we're going to set equal to 0 when x equals 20 centimeters, so 0.2 meters. Set that equal to 0. So go ahead and plug in 0.2 for x, and then solve for L, which is the only missing quantity here. And you can cancel out the Q2. So go ahead and do that on your own. Find out what the value of L is based on that. Take a minute, and we'll come back and take a look. OK, setting this equal to 0 and then cross-multiplying, you'll find the following algebraic equation. 4x squared equals L plus x all squared. And then squaring both sides, you just get 2x equals L plus x. So L ends up equaling x, actually. So L is 20 centimeters. All right, so that's how far these charges are separated. And again, we use the fact that the electric field was 0 at x equals 20 centimeters to find that. Now, the next step is we want to find out where is the electric field a maximum. And then this graph doesn't really tell you. It shows that it goes up, but it doesn't tell you what happens afterwards. It doesn't tell you when it becomes a maximum. Now, to find a maximum of any quantity, the rigorous way to do that, of course, is to take its derivative and set it equal to 0, and then check the second derivative to make sure it has the right sign. So what we need to do is find out the derivative of EX, and I want you guys to do it on your own. Let me just rewrite E in a little more simpler form. So I'll just factor out maybe the KE and the Q2. So for the first term, we have 4 over L plus x squared. And then for the second term, we have minus 1 over x squared. All right, so go ahead and on your own, take the derivative of this, set it equal to 0, and try to find out at what x value does the electric field have a maximum. Take a minute to do that now. I'll pause the video. When you're done, we'll take a look. All right, so here's our expression for the electric field. I went ahead and replaced 0.2 meters for L because we did find that L was 0.2 meters after all. Now we need to find the derivative of this, and taking the derivative, we'll find the constants stay where they are, of course. The derivative of the first term, this quantity is to the negative 2 powers, so bringing that down in front, you're going to have a negative 8 here. And the negative 2 power now becomes a negative 3 power, so you have 0.2 plus x to the third in the denominator. Oops. And then on this guy, you're going to bring down the negative 2, so you're going to have a plus 2 here divided by x cubed. We need to set that 0 to find the derivative. And so doing that, once we set that equal to 0, these two constants cancel out. The next thing we can do is divide the entire expression by 2, so you're going to have a minus 4 here and a 1 here. And then I'll go ahead and put that term on the other side. So carrying all that out in one step, we'll find that 1 over x cubed equals 4 over 0.2 plus x to the third power. Now we have x to the third power here, so the good thing is that both sides are to the third power, so the best way to do this is to just take the entire expression to the 1/3 power to cancel those out. And what you find here is that 1 over x equals 4 to the 1/3 power divided by 0.2 plus x. And this is just a linear equation, so if you go ahead and cross multiply, you can quickly solve for x, and you'll find that x equals 34 centimeters. All right. So that tells us that there's an extremum at x equals 34 centimeters. It does not tell us if it's a maximum or minimum. So to rigorously justify to yourself that this is indeed a maximum, you'd have to go ahead and find the second derivative of this. So in other words, take the derivative of the first derivative, and then plug in x equals 34 centimeters and find the sign. If the sign is negative, it should be a maximum. If it's positive, it will be a minimum. If you go ahead and do that, which I'm not going to do here, you'll find that indeed the second derivative has a negative sign, which means that it is a maximum and not a minimum. And that's in accord with what we see in the graph here. It looks like this thing kind of rises, and it looks like at x equals 34 centimeters, you should find a maximum, and then it'll start to decline again. All right, so that's the answer to the problem. We found, first of all, that the distance between these two charges was 20 centimeters, and then we used that to find out that the electric field has a maximum at x equals 34 centimeters, somewhere to the right of these two charges. Let me go ahead and summarize that in detail, and we'll come back and finish up. In this problem, we analyzed the electric fields due to 2-point charges. First, we found an expression for the net electric field due to the 2 charges. Then we set this expression equal to 0 at the x value indicated in the graph to find the distance between the 2 charges. Finally, to find the location of the maximum field, we differentiated the expression for e to the x with respect to x, and then set that equal to 0 to solve for x. So this is a pretty quick exercise in finding electric fields from point charges. It had some calculus, and we had a little bit of algebra involved as well. If you have any comments or questions, please leave that on the link attached to the video, and we'll see you next time.